Hello everyone, I'm Rekha Murthy, Assistant Professor, Department of Electrical and Electronics Engineering from Sai Vidya Institute of Technology. Today I'm here to explain related with the Module 2 of the subject Power System Protection, and the Module 2 relates with the overcurrent protection and a part of the distance protection. So the main outline today, what I'm going to discuss in this session is the introduction, time current characteristics, overcurrent protective scheme, reverse power or directional relay connections, and directional overcurrent relay. So these are the topics which I'm going to cover it up. The introduction. So as you know that a protective relay is nothing but it is the one which is going to operate whenever the load current is going to exceed a preset value. That is called as an overcurrent relay. So the value of this preset current above which the relay operates is known as its pickup value. So overcurrent relay is usually, it will be a cheapest and simplest form of protection. So these relays are mainly used for the protection of like distribution lines, large motors, power equipment, industrial systems, etc. So this overcurrent relays, they are also used in some of the sub-transmission lines. And scheme which we are going to incorporate for the overcurrent relay for the protection of this element of a power system, that is known as a overcurrent protection scheme or overcurrent protection. So this overcurrent protection scheme is going to include one or more the overcurrent relays. Now you can look onto this basic diagram. So where it is going to give an basic information that this overcurrent relays, they are being connected with the current transformer. This overcurrent relays will be connected with the current transformers. So whenever the CT is going to sense a high current from the preset value, the relay is going to operate, right? And it will actuate that trip call of the circuit breaker, and it will isolate to the equipment from the electrical system. And as I told, the scheme which you're going to employ, which you're going to incorporate with the overcurrent relay, that is nothing but called as an overcurrent protection scheme. So that is a basic introduction to this topic. Now let us move on with the time current characteristics. In the time current characteristics, depending upon to the time of operation, the overcurrent relays has been classified into the various groups. What are those? The first one is the definite time overcurrent relay, instantaneous overcurrent relay, inverse time overcurrent relay, inverse definite minimum time overcurrent relay, very inverse time overcurrent relay, extremely inverse time overcurrent relay, all this. So here, in this definite time overcurrent relay, this relay is mainly it is being created by applying a intentional time delay after crossing certain pickup value of the current. So we are going to provide the intentional time, so that after crossing the pickup value of the current. A definite time overcurrent relay, it can be mainly be adjusted to issue a trip output at a definite amount of time. Afterwards, it is going to pick up. So those it will have a time setting adjustment and pickup adjustment. Usually the attracted armature type of a relay with a time element is going to show this characteristics. So how exactly this characteristics looks like? Almost that is this one. So this is a definite time of a overcurrent relay, where we will provide some intentional value of a current, and after certain time the relay has to sense the fault. So that is going to detect the pickup value. Okay, now the next one, as I told, instantaneous overcurrent relay. Instantaneous overcurrent relay, that this relay is mainly operates as soon as the current in the coil gets higher than the preset value. Okay, instantaneously it will operate. It will operate as soon as the current in the coil gets higher than the preset value. There is no any intentional time delay set, so there is always an inherent time delay of the order, which will be in the order of few milliseconds. Here also the attracted armature type relays is going to show this type of a characteristic. So let me show you that this characteristic will just looks like this. Okay, immediately it will react upon. So there is a boundary which you can see that is a pickup value, maximum current where actually the relay has to sense the fault. If it is above than that, the relay has to trip. If it is below than that, then the relay should not trip. That is a boundary for this. Now, let me move on with the next type, that is the inverse time of an overcurrent relay. In the inverse time of an overcurrent relay, we will find that this inverse time is a this means that time of operation is inversely varies with the input current. So here you can see its characteristic. How does it looks like? This is what a characteristic. So this here this characteristic of like electromechanical induction disc relay is very suitable for this overcurrent protection. So in this relay, if the fault is more severe, it would be clear more faster. So that is a inverse time of a overcurrent relay. Okay. Next, coming to the inverse definite time. In the inverse definite time, definite minimum time overcurrent relay, and the very inverse time overcurrent relay and extremely inverse time overcurrent relay, all these three of them will be shown together. So where you will find in that case, in the IDMT relay, that is this type of a relay is going to give an inverse time current characteristic, which is at a lower values of the fault current, and definite time characteristic at a higher values of a fault current. Okay, so that means this is a combination of the inverse time current characteristic and also a definite time characteristic. So inverse time current characteristic will be given at a lower values of fault current, and a definite time characteristic at a higher values of fault current. Okay, that is about the IDMT relay. So you can see the characteristic here, which will be a comparison of three of these, that is very inverse time and extremely inverse. So in this case, you will find that IDMT will be above. At the first you will be having a IDMT characteristic. Below that will be having a very inverse time, and below the very inverse time, we will be provided with the extremely inverse time. So in very inverse time overcurrent relay, what will happen is a very inverse time overcurrent relay will give more inverse characteristic than that of a plain inverse relay or IDMT relay. Okay, so its time current characteristic will be lying between an IDMT characteristic and extremely inverse characteristic. Okay, similarly in the case of like extremely inverse time current characteristic, in that extremely inverse time over current relay, it is going to give a time current characteristic which is more than the inverse than that of the inverse time and the IDMT relays. Okay, so that is a very extremely inverse time. And very inverse relays usually fail in selectivity, and extremely inverse time relays are usually employed at that time. Okay, that is about the special, all these characteristics of the relays. Now coming to the next topic. So in the next topic, it relates with the overcurrent protection schemes. So in the overcurrent protection schemes, they are widely used for the protection of the distribution lines. They are widely used for the protection of distribution lines. If you consider, like if the fault occurs something, there will be three sections of a lines which I'm going to sectionalize, like A, B, C. Okay, so these will be the sections of the lines which you are going to consider onto the feeders, which you can see that a feeder may be sectionalized and two or more overcurrent relays will be used. Okay, so let us assume that there will be three sections. If the like called as A, B, and C, if the fault occurs beyond a C, okay, beyond the C, and make sure that everywhere in each of the section we have provided with the circuit breaker, right? First the circuit breaker has to sense, first the relay has to sense the fault and it has to give a command to the circuit breaker, right? Then only we can isolate the fault. So if a fault occurs beyond a C section, then the circuit breaker at the substation C only should trip, not the other. The circuit breakers at A and B should not trip, as far as the normal operation is concerned. Okay, so suppose if the relay at C is going to fail to operate, then the circuit breaker at B should trip as a backup protection. Similarly, if the fault occurs between the B and C, the circuit breaker at B should trip. The circuit breaker at A should not trip. Suppose if there is a failure of a relay at the section B, then the relay A should trip. So like that, it will be seen that the relays must be selective with each other. So for this proper selectivity of the relays, we need to consider the schemes depending upon to the system condition. What are those schemes? The first is time current graded system and a combination of both time and current grading. Now let us discuss what is this time graded system. In this scheme, the definite time overcurrent relays will be used. So when a definite time relay is going to operate for a fault current, then it starts a timing unit which trips the circuit breaker after a preset time, which is quite independent of the fault current. So here, the operating time of the relays will be adjusted in an increasing order from the far end of the feeder. Okay. Now let us see here the difference in the time setting of the two adjacent relays are usually kept at around 0.5 seconds. Now this difference is to cover the operating time of the relay and the errors in the relay and CT. Now let us see here that with the fast circuit breakers and modern accurate relays, it may be possible to reduce the time further to around 0.4 seconds also, or it can be a 0.3 seconds. Now let us take these three sections and analyze. Whenever a fault occurs beyond the C, when the fault occurs beyond a C, then all the relays will come to an action as the fault current flows through all of them, of course, right? But here, what will happen? The least time setting is where do you find the least time setting? It is at the C point, at the C. So it operates after 0.5 seconds and the fault is cleared. Now the relay A and B are reset. A and B are reset. Okay, that is how the operation takes place. If the relay C fails, Okay, then the fault will remain uncleared. In that situation, what will happen? In that situation, which is the least time taken between the A and B, that is here. Comparatively to the 1.5 second, we will consider 1 second. There, the relay at B will operate and the circuit breaker at B will trip. Okay, if the circuit breaker B also fails, suppose if this also fails, then after 1.5 second, the circuit breaker A will trip. But what is the drawback of this scheme is that for the faults near the power source side, the operating time is more, right? Do you agree? Operating time is more towards that power side, that is around 1.5 seconds. But here it is at the last towards the load, it is 0.5 seconds. So if the fault occurs near the power source, it involves a large current. Hence, it should be cleared very quickly. But in this scheme takes the longest time in clearing the heaviest fault, which is found to be undesirable because the heaviest fault is the most destructive. So this scheme is suitable for a system where the impedance between the substations is low. Okay, fine. So this is all about the time graded system. Next, coming to the current graded system. So in a current graded system, this scheme, the relay are set to pick up at progressively higher values of the current towards the source. So the relays employed in this scheme, they are high set, or you can say it is a high speed instantaneous overcurrent relays. And here the operating time will be kept the same for all the relays which is used to operate, which is used to protect the different sections of the feeders. Here the current setting of the relay, which mainly corresponds to the fault current level for the feeder sections which has to be protected. Now let us consider this example, wherein here the we can see here the relay at B should trip for the fault anywhere between the B and C, but it should not operate for a fault beyond C. Do you agree? That is ideally. Similarly, relay at A should trip for a fault between the section A and B. The relay at C should trip. The relay at C should trip for a fault beyond C. That is all ideal operation. But this ideal operation is not achieved. Why? Because of many reasons. Because the relay at A is not able to differentiate between the fault, whether it is very close to B, which may be either on the either side of the B. If the fault is in the section BC, which is very close to the station B, then the relay A understand that it is in the section AB. This happens only when there is a very little difference in the fault current. If the fault current occurs at the end of the section A and B or in the beginning of the section BC. That is one point. Second thing, the magnitude of the fault current, it cannot be accurately determined as all the circuit parameters may not be known to you. That is second point. Third point is, during a fault, there is a transient conditions and the performance of the relays which is not so accurate. So because of these three reasons, we need to obtain a proper discrimination. So relays are set to protect only a part of the feeder, usually about 80%. That is why this scheme cannot protect the entire feeder. This system is not used alone. So it may be used in conjunction with the IDMT relays. That is what we can see here. So the performance of the instantaneous relays is affected by the DC component of the transients, which I have shown in the first figure. So the error is been introduced by that whatever the DC offset components, which has been causes the relay to get overreach. So you will find there will be a higher value of X by R ratio, and which will be of a great problem to the system. So a DC filter is mainly used to overcome this problem, right? Um, so this is how about the current graded system. So this scheme is used where the impedance between the substation is sufficient to create a margin of difference in fault currents. So the advantage of the system as compared to that of a time graded system is that the operating time is less, near to that of a power source. That is what the advantage of this. Okay. Now coming to the combination of current and time grading. This scheme, combination of a current and graded grade, in that scheme is widely used for the protection of the distribution lines. ITMT relays are usually employed in the scheme in the case of a combined cases. So they have a combined features of both the current as well as a time grading ITMT relays, which will have a current as well as a time setting arrangements. So the current setting of the relay is made according to the fault current level of the particular section to be protected, and the relays are set to pick up progressively at higher current levels towards the source side, and the time setting is also being done in a progressively increasing order towards the source side. The difference in the operating times of two adjacent relay will be kept around 0.5 seconds. That is how about the combined combination of both the current and time grading system. Okay, so this is what about the time grading, current grading, and the combination of both. Now let's go next part of a new topic, that is the reverse power or a directional relay. So let me consider a diagram where this is a electro so here the fluxes, two fluxes from both of these, each of the quantities, that is flux psi1 and psi2, and eddy currents with psi2. Okay, so here the flux psi1 and here the flux psi2 will be produced, and both will interact in such a way that it is going to produce a torque. So similarly, the flux psi2 also induces some eddy currents in the disk, which will interact with the flux psi1, and it is going to produce a torque. So that resultant torque is going to the torque which is the torque which is produced, it will be proportional to that of both of these quantities, because due to these two quantities only flux can be produced, right? So therefore the torque will be proportional to V into I into cos phi, where psi is nothing but it is a phase angle between the V and I. So the torque is maximum when the voltage and current are in phase. So in order to produce this maximum torque during the fault condition, when the power factor is very poor, then we are going to make use of a compensating winding, and also the shading coils will be provided in order to make the maximum torque during the fault conditions. The power factor will be very poor. That is why a compensating coil circuit and as well as a shading coil will be provided here. Okay, as we had discussed in the previous modules, that torque which is produced by an induction relay will be given by T is equal to psi1 into psi2 into sine theta, which is directly proportional to that of I1 into I2 into sine theta, where the flux psi1 and psi2 are the fluxes. Okay, and the angle which is between the psi1 and psi2 or I1 and I2, it will be theta. If one of the actuating quantity is voltage and the current flowing in the voltage coil, it is going to lag behind the voltage by an angle of 90 degree. So let us see that phasor diagram. Assume that here let us say the voltage V and the current I1, which is flowing in one of the coil, and that is nothing but the current coil, that is a lower part of the U-shaped electromagnet. So that is the current I, and I2 is again further lagging behind the voltage V. The load current I1 lags the V by an angle of psi. Then the angle theta between the I1 and I2 is also equal to 90 degree minus psi. So due to this, we will get a torque equation as I1 into I2 into sine of 90 degree minus psi, which is again directly proportional to that of I1 into I2 into cos psi, which is nothing but again it is directly proportional to that of V into I cos psi. Okay. So here an induction, let's move on with an induction cup type of construction, where the induction cup type of a directional relay that is also used to produce a torque which is proportional to that of Vi into cos phi. So let us go through that type of the directional relay. Okay, this is an induction type. Here, two opposite poles. This is one and this is another two. This is north and south, and here also north and south. So two opposite poles are energized by the voltage coil, and the other two poles again they are energized by current, which you can observe here. Here voltage is a polarizing quantity. And the polarizing quantity is the one which is going to produce one of the two fluxes. The polarizing quantity will be taken as a reference with respect to the other quantity, which is nothing but a current in this case. Okay, which is nothing but a current in this case. Now, the interaction of these two quantities, again the flux will be produced, and you will find there will be an interaction between the two fluxes. Then the torque will be produced. Torque which is produced is positive when the power factor is positive. That means the value psi should be less than the 90 degree. Whenever you find the psi is more than the 90 degree, then the torque will be negative. How it is, you can see. For example, this is what the voltage be, which we have taken it as a reference. And here you are going to get the normal condition. We will find that the negative torque is produced. How? See here, what will happen at a particular relay location when the power flows in the normal direction, the relay is connected to produce a negative torque. And the angle between the actuating quantities which is being supplied to the relay, it will be kept around 180 degree minus psi to produce a negative torque. So if due to any of the reason, the power, whenever the power flows in the reverse direction, the relay is going to produce a positive torque and it is going to operate. So in that condition, the angle between the actuating quantities psi should be kept less than the 90 degree in order to produce the positive torque. So what you observed is at the normal condition itself, it is going to produce a negative torque. Whenever there is an abnormal condition, the relay will start to operate and it is going to produce a positive torque. So for a normal flow of power, the relay is supplied with the V and the current minus I. Okay. For a reverse flow, the actuating quantity is becoming V and I. That's all. Positive I. Then the torque is becoming V into I cos phi. That is what the positive. So this can be achieved by easily reversing the current coil. How to reverse that current coil? Which you can see here. Okay, so this is how in this fashion we are going to connect the to produce a negative torque initially. So here the relaying units is going to supplied with the single actuating quantity which we have discussed earlier, and This is what about the reverse power or a directional relay. Okay, so make sure that at the abnormal condition, we want a torque which is to be produced. It should be V into I cos phi. We don't find any negative symbol. It is almost positive. That means at the abnormal condition, we are getting V into I cos phi. But at normal condition, we have to assume that the current or the power is flowing in the reverse order. That is minus I. That is what you can see in this phasor diagram. Okay, that is what the meaning of having a reverse power or a directional relay. Next, coming to directional relay connections. See, whenever we find there is a close-up fault occurs, the voltage usually becomes low and the directional relay may not develop a sufficient amount of torque for its operation. Under that condition, what will happen under that fault condition? The power factor will be very low, due to which there will be insufficient amount of torque. If the relay is connected in a normal way to develop a torque which is proportional to V into I cos phi, then these type of problems can be overcome. But to get a sufficient torque during all the types of fault, with irrespective of the locations, with respect to the relays or the relay locations which is to be modified, so each relay is energized by the current from its respective phase and the voltage from the other two phases. So how to do that? So there are two methods of connections. One method is known as a 30-degree connection and the other one is called as a 90-degree connections. So in 30-degree connection means the current coil of the relay of phase A is energized by a phase current IA and its line voltage is V A to C, V across A to C. Similarly, the relay in B is energized by the current IB and the voltage is V with the B to A. Similarly, the relay in phase C with the current IC and the voltage is V C to B. This is what we can see in the phasor diagram. So the relay will be designed in such a way that to develop a maximum torque when its current and voltage are in phase. So this condition with the present connection can be satisfied whenever the system power factor is around 0.8666 lagging. Okay. Next, coming to 90-degree connection. 90-degree connection is much better. It is going to give a better performance under most of the circumstances. So in this connection, the relay in the phase A is energized by the IA and the voltage will be from B to C. B to C. Earlier it was A to C. Now it is B to C. Similarly, B phase relay by B is getting energized by the current IB and the voltage is from C to A. Similarly, for the C relay, it is also energized by the IC and the voltage is from A to B. So like this, the relays will be designed in order to develop a maximum torque. So when the relay current is going to lead the voltage by around 45 degree and it will have some internal compensation. So for all the types of faults, L to L, L to G or 2 times of L, 2 L to G, 3 phase and the phase angle will be seen by the relay. It should be well below the 90 degree. So this connection is going to ensure the adequate voltage polarization except for a 3-phase close-up fault when the voltages on all the phases becomes very small. So this is about the connections. Next, coming to the directional overcurrent relay. In this directional overcurrent relay mainly operates whenever the current is going to exceed a specified value in a specified direction. So it contains 2 relaying units here, which you can see. One is the overcurrent unit and the another one is the directional unit. For the directional control, the secondary winding of the overcurrent unit is kept open. So when the directional unit operates, It closes the open contacts of the secondary winding of the overcurrent unit. So thus we can see that a directional feature will be contributed to the overcurrent relay. So the overcurrent unit may be either it can be a wattmeter type or it can be a shaded pole type. So in a shaded pole type, the opening is made in the shading coil, okay, which is in this case a wound coil instead of an ordinary copper strip. So this is what about the directional overcurrent relay. So in next session, I'm going to discuss about the protection of the parallel feeders and protection of the ring mains and also some of the earth fault and phase fault protection. Thank you for watching this video.